Welcome to The Explainer. Today, we're unpacking the technology at the very heart of the quantum computing revolution, the superconducting qubit. We're going to follow its journey, from what was basically a wild thought experiment all the way to a real-world tech that's already giving our best supercomputers a run for their money. Let's jump in.
You know, it all really started with this one question from Nobel laureate A.J. Leggett. And he wasn't really talking about cats, of course. He was throwing down a challenge to physicists. Can we actually see the strange, bizarre rules of the quantum world, not just in tiny little atoms, but on a scale big enough for us to see and build and control?
So this wasn't just some abstract thought experiment. It sparked a real dream. A dream to build an entirely new kind of machine that runs on these macroscopic quantum effects. But to even get started, they first had to solve a massive paradox, something right at the core of quantum engineering.
And here's the fundamental dilemma. Think about it. On one side, you've got tiny things, like atoms. They are naturally quantum, perfectly shielded from the noisy world around them. But try wiring them together. It's incredibly hard. Then, on the other side, you've got big things, like electrical circuits. Super easy to build, easy to connect. But they act like tiny antennas, soaking up all the noise from the environment, and that noise just kills any quantum behavior. The trick was somehow getting the best of both worlds.
So to build this paradoxical machine, engineers were going to need a whole new kind of tool, a new electronic component, something that just didn't exist in our classical world. They needed a secret ingredient.
Okay, so here's the recipe for a quantum circuit. First, you need absolutely zero electrical resistance. Easy enough, you just use superconductors. Second, you got to get rid of all the heat, all that thermal noise, so you cool the whole thing down to temperatures colder than deep space. But there's a third ingredient, a really crucial one, that your average circuit just can't provide.
And here's the problem. A simple quantum circuit, which is kind of like a tiny superconducting radio tuner, has this energy spectrum that looks like a perfect ladder. You know, all the rungs are spaced exactly the same distance apart, so if you try to ping it with a signal to go from the bottom rung to the first rung, you accidentally also make it go from the first to the second and the second to the third and so on. You can't talk to just one transition. You can't isolate a 0 and a 1.
The solution, the magic ingredient, is this thing called a Josephson junction. It is the only electronic part we know of that is both nonlinear, meaning it can break that perfect ladder, and non-dissipative, meaning it doesn't leak energy and destroy the quantum state. It's the whole ballgame.
And what's wild is how simple it looks. I mean, it's basically just a sandwich, two superconductors with a super thin insulator squished in between. This tiny little thing is what lets a circuit that we built behave like a giant artificial atom.
So this is the key. In a normal wire, the relationship between current and energy is straight, it's linear. But inside a Josephson junction, that relationship is a sine wave. And this nonlinear behavior is what actually warps the energy ladder, kind of scrunching the rungs closer together the higher you go. That makes the gap between level 0 and level 1 totally unique. And boom, now you have a qubit. So, with the Josephson junction finally in their toolbox, scientists built the very first quantum circuits back in the late 90s. And it was a huge deal, a massive achievement. But they were also unbelievably fragile. They were in a constant battle against all that environmental noise.
At first, there were two main approaches. You had the charge qubit, which was basically a tiny island for pairs of electrons. And you had the flux qubit, which was a tiny superconducting loop. The big problem was, the charge qubit was ridiculously sensitive to any stray electric field, and the flux qubit was just as sensitive to stray magnetic fields.
So, yeah, they proved the idea worked. You could build one of these artificial atoms. But their coherence times, that's the lifespan of the quantum information, were measured in nanoseconds. It was like trying to do your taxes in the middle of a hurricane. To do anything useful, they first had to figure out how to tame that storm.
And then, in 2007, a new design came out of Yale University that completely changed the game. It was an absolute breakthrough that basically solved the noise problem with what seemed like a really simple tweak.
Meet the transmon. The idea was just brilliant. You take a charge qubit, the one that's super vulnerable to charge noise, and you just add a big capacitor right next to it. And this one change made the qubit exponentially less sensitive to that noise. Sure, you gave up a tiny bit of that nonlinearity we talked about, but the gain in how long the qubit stayed quantum, it was just enormous.
And the impact was immediate and dramatic. Coherence times went from just a few nanoseconds for those first charged qubits to tens, and then hundreds of microseconds for the transmon. We're talking a 100,000-fold improvement. This design is what really unlocked the door to building much bigger, much more stable quantum processors.
So thanks to the transmon, we finally have qubits that are pretty robust. And that's brought us into the era we're in right now, a time that's defined by both incredible power and, well, a little bit of imperfection.
And this is what a modern quantum processor actually looks like. It's this beautiful, intricate chip that hosts dozens of these transmon qubits, all wired together with tiny transmission lines, ready to perform calculations that, not too long ago, were purely theoretical.
We call this the NISQ era. That stands for Noisy Intermediate Scale Quantum. We can build processors with 50 to 100 qubits, which is an amazing scale, but they're still noisy. Errors creep in a little too fast for the kind of error correction we really want. So the whole game right now is to find valuable, important problems that these imperfect machines can solve anyway. And they're already tackling some incredible stuff. We're talking about simulating the behavior of really complex molecules, which could completely change how we discover new drugs and invent new materials. And they can also take on these abstract computing challenges that are designed specifically to prove just how powerful they really are.
Which brings us to a real watershed moment. Back in 2019, Google's Sycamore processor did this one, very specific task in just over 3 minutes. Now, it was estimated that the most powerful supercomputer in the world would need about 10,000 years to do the same thing. That was it. That was the first clear demonstration of a true quantum advantage.
So, achieving quantum supremacy was a monumental milestone, for sure. But it is not the end of the story, not by a long shot. To build a truly universal quantum computer, one that can solve any problem we can dream of, there is one last grand challenge left.
And that next frontier is called quantum error correction. The basic idea is to take many of these pretty good but still noisy physical qubits and kind of weave them together into a single, perfect, logical qubit. This new encoded qubit can then detect and correct its own errors, basically protecting the quantum information from noise forever.
And so, we've come full circle. We started by asking if we could build Schrödinger's cat in a lab, and the answer, today, is a definite yes. We've built these incredible quantum machines that can already do things no classical computer on Earth can touch. The next great leap, the next dream, is to make them perfect. The quest for the fault-tolerant quantum computer is on.